So our primary idea today, the thing that we're going to spend most time doing, is looking at questions like this. When do we know that our reaction has actually taken place in a solution? And the reason we have to ask this question goes back to what we were talking about on Friday and in lectures before that. Since we know that ionic compounds, or any electrolyte for that matter, is going to break apart into ions once it hits that water, then when we look at a normal chemical equation, we have to understand that what is represented in that molecular equation doesn't really reflect what's actually going on inside that solution. So let's take, just as an example here, a common reaction in solution where we've got potassium nitrate reacting with calcium hydroxide to make potash, potassium hydroxide and calcium nitrate. This chemical equation would seem to indicate that something's going on when I put those two solutions together. The reality of the situation, though, is there's no actual chemical reaction taking place here. And the reason why, this is a solution full of ions. This is a solution full of ions. When I put those two solutions full of ions together, they have to give me something other than a solution of just ions. Otherwise, what can we really say has changed? So there are some clues, some markers that we look for to help us to indicate whether or not a chemical change has occurred and whether that chemical change actually is a chemical change, or is it just a creation of a larger solution like it is in this case? So what are the things that we look for? Well, since most of our reactions in aqueous solution are going to fall into one of the replacement categories, what we need to look for are two kind of telltale signs. So in single replacement reaction, obviously we're going to see the formation of a new solid element or a new gaseous. We're going to see some kind of change where one element goes into solution and a new one pops out. Those are pretty easy to see. It's the double replacement reactions we have to watch out for. In those double replacement reactions, I got a solution of ions coming together with another solution of ions. And how do I know whether or not those ions actually changed at all? Well, luckily for us, the double replacement reactions that we're interested in fall into two categories. One of them is called a precipitation reaction. The other is an acid-base reaction. For precipitation reactions, what we are looking for is the formation of an insoluble solid product. So in this particular case, I've got silver nitrate reacting with sodium chloride to make sodium nitrate and silver chloride. If I were to take these two solutions and put them together, I would immediately see the formation of a white solid. That white solid being the sodium chloride. Why would I see that? Well, because it comes back to our solubility rules. Chlorides are usually soluble in water, except with lead, mercury 1, and silver. Silver chloride being one of the products of this reaction. we would anticipate based upon the solubility rules that it comes out of solution, that it forms a solid. So the use of our solubility rules can actually help us to predict, okay, this solution, silver nitrate, is going to be soluble. This solution, sodium chloride, is also going to be soluble. The sodium nitrate that forms, also soluble. The silver chloride that forms, well, that one's not soluble, that one's different. That marks a difference between the reactant side and the product side. And since we have a marked difference between the two, that's our evidence that a chemical reaction actually occurred, even if we don't actually do the thing in the lab in the first place. We can follow this story through the use of something called a net ionic equation. More on that in a second. The other type of reaction is one that we kind of started to look at in the last lecture, the acid-base reaction. In an acid-base reaction, we get two things. Ordinarily, we get some sort of salt formed from the cation of the base and the anion of the acid. That salt could be soluble, it could also be insoluble, it just depends upon what's being brought together. And your solubility rule certainly would help with that. And the other thing that is formed usually in these cases is water. Water is a molecular compound, and by definition, a non-electrolyte. So out of two very electrolytic substances, I get a non-electrolyte, that's a sign of a chemical reaction. That's a sign of a chemical change. So those are the two types of reactions that we look for in solution, and based upon their results, we would be able to determine, oh, this is a balanced chemical equation, this is a neutralization reaction, I can see a unique product coming out of those reactants. It is especially more difficult to see that in the first kind, the precipitation. You gotta know your solubility rules. You gotta know how to predict what's going to dissolve and what's going to remain a solid. To help us along the way here, we have to take aqueous solution chemistry and separate it from what we've done in the past. Everything that we've talked about as far as chemical reactions thus far in this semester has been on the molecular level. This molecule reacts with this molecule to make these new molecules. Hydrogen gas reacts with chlorine gas to make hydrogen chloride gas. And up until this point, that has worked, because there have been noticeable differences. We can look at differences in the bonding. We can look at differences in the physical and chemical properties of the reactants versus the products to help us see, okay, that was definitely a chemical reaction. But in aqueous solution, we don't have that luxury, because oftentimes the solutions all look the same. Here's a white solid that dissolves into water, and the resulting solution is clear and colorless. And here's another white powder that dissolves into water and gives us a clear and colorless solution. And when I put them together, they give us a clear and colorless solution. Without the use of ionic equations, I have no way of determining heads or tails. My physical examination of the reaction gives me nothing to work on. When I look at the chemical equations, at least initially, doesn't give me a whole lot to work on. But an ionic equation solves that for us by saying, okay, in this particular case, ions and chloride ions. That second clear colorless solution, it wasn't potassium nitrate, it was potassium ions and nitrate ions. And when I put them together, here's what I would expect. Based on my solubility rules, I expect to see this. Ionic equations help us to solve this problem. Now the question becomes, how do we end up making ionic equations to help us solve this problem? If you know your solubility rules, if you know how to identify acids and bases and classify them into strong and weak categories, this is not a terribly difficult process. If you struggle with the solubility rules, if you have trouble identifying weak acids versus strong ones, this can be a very difficult and trying process for you. Which is why we had that assignment 8.1 over the weekend. Which is why we're doing the solubility rules proficiency on Friday. You need to know how to do these things, how to evaluate in a snap, so that you can properly make the ionic equations. And there's some other little tips and tricks and things that come along with for the ride as we go. But the first thing that we do is the same that we've always done. We start with the molecular equation. We're going to add one little note to this. Start with the molecular equation and balance it. Ionic equations are pretty useless to us unless they are balanced. More on that in a minute. From the molecular equation, you do exactly what you did in that assignment on Friday night. You classify. This is an acid, this is a base, this is a salt, these are the types that we're dealing with. The reason why is because we need to know what are strong electrolytes. In our molecular equation, we need to know what's going to break apart and what's going to stay together. Anything that is a strong electrolyte is going to break apart into its ions that make it up. So again, strong electrolytes, what we were talking about there, these are your soluble salts. Your strong acids, and your strong bases. If it fits into any of those three categories, it's a strong electrolyte, it's going to split up into ions. If it's in any of the other three remaining categories, weak acid, weak base, insoluble salt, gas, molecular compound, anything that we know doesn't conduct electricity, it's going to stay together in its molecular form. And so that's how we turn a molecular equation, the one that we've been working with, the one that we're familiar with, and turning it into an ionic equation. Now, there is one further wrinkle in this that we want to look at and need to discuss. As you might expect, when we convert those electrolytes into ions, there's going to be some common ground in those equations. We know from our solubility rules, nitrates, for example, are always soluble in water. So chances are pretty good that if I have a nitrate compound on the left, there's going to be a nitrate compound on the right. And because the nitrates are always soluble, that means that we're going to have nitrate ions on both sides of the equation. Anytime that happens, what we are viewing is something called a spectator ion. Spectator ions are exactly what the name implies. Just like spectators at a sporting event or at a theater production, concert, whatever, they sit and watch. They don't actually participate. So spectator ions are there, but they really don't do anything. And since they really don't do anything, as we convert our ionic equation to a net ionic equation, we remove all of those things that aren't doing it. The net ionic equation only contains the stuff that actually reacts, the stuff that actually changes. And so that's where this last line is really important. If a net ionic equation, if we go to the ionic equation, nothing's changed. Every ion that was on the reactant side shows up in the product side. That's our clue that nothing happened. That's our clue that nothing changed. And so in that kind of case, when nothing changes, the reactants look exactly the same as the products, we have a word for that. It's called no reaction. Nothing actually happened. And so this is where those ionic equations become useful to us. Because unlike that first example I gave you, where you look at the equation in the molecular form and say, yeah, that makes sense. It's a double replacement reaction. I get two new products out of this. In the ionic world, we know that all that happened was those ions just combined with each other. We end up making a bigger solution than we had before. But in terms of the chemistry, not a thing changed. Nothing happened. All right, let's take a look at an example. In this example, we have silver nitrate reacting with potassium chloride to give us silver chloride and potassium nitrate. Now, the first thing that we want to do, we want to make sure that this particular equation is balanced. And it is. This is one of those 1-to-1 to 1-to-1s. So the next thing that we need to do is we need to classify. Put all of these things into groups and then start to break apart the things that are strong electrolytes. So silver nitrate. By virtue of this nitrate ion, we know nitrate ions are always soluble in water. We know that silver nitrate is a soluble salt. Potassium chloride, by virtue of that potassium ion, all of our alkali metal ions, all of those in the first group of the periodic table are soluble in water. Potassium is in that first group, so potassium chloride, also soluble. Silver chloride. We know that most most chloride compounds are soluble in water. The three exceptions, Merle's chlorides, mercury 1, lead, and silver. Ag is silver, so that's one of the exceptions. This is an insoluble salt. So we're going to mark that as IS. Last one, Potassium nitrate, both of the ions in this one are on our always soluble list, so this one is going to be soluble also. So we've now established the character of all four of those compounds. Now we need to go about the production of splitting apart the ones that are strong electrolytes. In this case, that'd be all the ones that are soluble salts. So silver nitrate, we're going to split into the silver ion, Ag+, and the nitrate ion, NO3-. Potassium chloride, we're going to split into the potassium ion, K+, and the chloride ion, Cl-. Silver chloride is insoluble. If it is insoluble, or a weak acid, or a weak base, or another kind of non-electrolyte, it stays together. It doesn't separate. So this one is just going to go in as AgCl. For potassium nitrate, again, soluble, so it's going to split into its ions, the potassium ion, K+, and the nitrate ion, NO3-. So this is our ionic equation. Everything that was soluble, everything that would be in ionic form inside of that solution is now shown as ion. Now we need to go about the process of removing the spectator ions to turn this ionic equation into a net ionic equation. So I can look at this and see, okay, I've got nitrate on the one side and on the other. I've got potassium on the one side and on the other. Those cancel. My net ionic equation is just going to be the silver ion and the chloride ion, making silver chloride. That's all that's taking place inside of this solution. But because we can identify what is actually reacting, we can identify that there is a chemical reaction that would occur when I put these two solutions together. Now, depending upon the source, you might see where you have to add phases to these to help identify where they are, what kind of phase they're holding. Anything that is ionic is going to have to be aqueous. So from the very beginning, these three substances that we identified as soluble salts, all three of them would have aqueous designations. If it dissolves in water, then that's what it is. It's aqueous. It's dissolved in water. That's what aqueous means. The insoluble silver chloride, if we see insoluble things, they're going to come off as solids. For molecular compounds, when these come up, especially in neutralization reactions, what we'll find is that they are either going to come off as gases or they're going to come off as pure liquids. Really, the big difference, honestly, Water is the one that usually comes off as a pure liquid. Almost everything else comes off as gas. All right, questions about this particular example? All right, let's move on then. Let's try another one. Here we are told that a precipitate forms when aqueous solutions of ammonium sulfate and calcium chloride are mixed. What is the net ionic equation? So a couple of things that we have to do here. We have to, first of all, determine the formulas of the two solutions, figure out what the products are, do the double replacement, balance it all up so that we can get the molecular equation. All right. From our net ionic, from our polyatomic ion sheet, we should know that ammonium is NH4+, and that sulfate is SO4 -2. So if I do a crisscross there, my ammonium sulfate would be NH4 taken twice, SO4. For calcium chloride, I've got the calcium ion. Calcium, if I look on the periodic table, it's in group 2. All the group 2 ions are +2 ions. Chloride is Cl. It's a halogen, group 17. All the group 17 ions are -1s. So if I do my crisscrossing there, I end up with calcium chloride, CaCl2. Now we're told both of these are aqueous. So we can put in those tags there to help us initially. This is a double replacement reaction. Remember, double replacement reactions, we are going to see cation switching. So the ammonium ion is going to switch sides with the calcium ion. I end up with NH4, which has a +1 charge, and chlorine, which has a -1 charge, +1 and -1. That means that we're already balanced. NH4Cl is going to be the product. The secondary product here, I've got calcium, Ca2+, interacting with sulfates, SO4 2-. Again, charges match, so it's a 1-to-1, CaSO4. Now, we're already told that a precipitate is forming here. Question is, which one is the precipitate, or do we have a rare circumstance where they're both precipitates? We can look at the formulas. Ammonium is on that always soluble list. So this is going to be a soluble salt, which means that this is aqueous. Sulfates are on the usually soluble list, except for the Balcomers sulfates, where Balcomers refers to the bottom half of group 2 plus lead and mercury. The bottom half including calcium, strontium, and barium. Calcium being one of those exceptions. This is an insoluble salt. So the phase here would be solid. Finish off the classification, because we know these two are aqueous already, we also know that they are soluble salts in both cases. So now I've gone through, I have my chemical equation. It's not balanced yet. I've got my chemical equation, and I've classified all the ingredients in that equation. Now to balance it, it's actually not that hard. I have 2 chlorides and 2 ammoniums. So I just needed 2 right there. That was the only thing that needed to be balanced. Now I need to do a conversion. Now I need to take this molecular equation and turn it into an ionic equation. This is where we can run into problems. Last one was kind of easy. Everything was 1 to 1 to 1 to 1. This one's not so. What do I do with subscripts like this after the ammonium? What do I do with coefficients like this in front of the ammonium chloride? How do those come out in my ionic equation? This is where a real intimate knowledge of those polyatomic ions helps. Because there should be no ions in your ionic equation that you don't recognize from somewhere else. What I mean by that is this. One of the most common mistakes that people make is just copying. Okay, that's what I need for the ammonium and for the chlorine. I haven't taught you any ion that looks like this, where it's 2 ammonium ions stuck together. I haven't taught you anything about a chlorine molecule with a -1 charge. Those subscripts are going to get converted. And what they're going to get converted into are coefficients. So that subscript of 2 around this ammonium, that's getting pulled out. It's 2 ammonium ions, 2 NH4 pluses in the aqueous state. It's 1 sulfate ion, SO4 -2 in the aqueous phase. It's 1 calcium ion, Ca+2 in the aqueous state. This subscript on the chlorine gets pulled out also. It's 2 chloride ions in the aqueous phase. So that covers when I have balancing subscripts. That is, subscripts that are there to help balance the chemical formula in terms of its charge. Notice, I didn't do anything with the 4 here in the NH4. That's part of that ion. I didn't do anything with the 4 here in the sulfate ion. That's part of that ion. The only one that I moved to the outside was this one on the outside. Now with coefficients, you do the same thing, only you apply it to both of the ions inside of that compound. So sometimes it's helpful to kind of split, just to remind yourself, this is the cation, this is the anion, this is what I need to do. So I have 2 ammonium ions, NH4+, still in the aqueous phase. I have 2 chloride ions, also still in the aqueous phase. Calcium sulfate is insoluble, so we're going to leave it as just that. Calcium sulfate, solid. Why that is so important, why that gets stressed so much, is relatively simple. If I don't do things that way that I just showed you, I'll never identify the spectator ions correctly. Because if I have chlorine 2 with a -1 charge here, and I'm balancing against the chlorides here, notice that that would be a mismatch. this is not the same as this. If they are not identical to each other, they can't cancel out because they're technically different, both in terms of their chemical state and in terms of their charge state. So we need to be careful about that. And this is where the majority of mistakes get made in doing these balanced chemical equations from an ionic standpoint. Now we need to identify spectators. I can see that I have 2 chlorides on the reactant side and 2 on the product side. I've got 2 ammoniums on the reactant side and 2 on the product side. Those are going to cancel. All that is left over is the calcium ion, the sulfate ion, and the calcium sulfate. My net ionic equation is going to be the sulfate ion in solution reacting with the calcium ion in solution to make calcium sulfate, which is insoluble. All right, any questions about this example? All right, you probably know what's coming next. If you haven't been paying attention the last 10 weeks. You gotta do one. All I'm looking for here is the net ionic equation. I've already balanced the equation for you. I just need the net ionic. Now, if you get to the net ionic part and everything's canceled out, type in no reaction. Otherwise, use the formula tool inside of Top Hat. You should be able to make subscripts and superscripts using the text editor. You do not need to include the phases. second compound is sodium iodide, I minus, which means the last one led to iodide, just in case you didn't recognize the sans serif on there. All right, ladies and gentlemen, sometimes it is the littlest of details that can just make this whole thing fall apart. That's one of the reasons why we're spending 2 days on it, because we want to try to catch as many of the little things as we can so that we know to look out for. So let's take a look. So you should have been able to identify the nitrate here makes this soluble. The sodium here makes this one soluble. The sodium and the nitrate in this one make it soluble. Once we identify that this is iodine, PbI2, we should be able to identify also that this is an insoluble solid. Iodides follow the same rule as chlorides. The Merle's rule: mercury, lead, and silver. So from that perspective, this is my insoluble solid. I need to break this apart. So breaking it apart, I get this. Quick trick for you. When you have subscripted stuff like this, remember when we did nomenclature, we did that crisscross rule to turn the charges into subscripts. We can go the opposite way now. To get the charge that we need, we can go back. So the lead is a 2 positive, the nitrate is a 1 negative. Sodium and iodide, we would just pull from the periodic table. But we need to make sure that we remember that 2 out in front goes over both of them, not just the one of them. Same thing for the sodium nitrate, 2 sodium ions, 2 nitrate ions. One thing that's important to note also, these equations, if they are double replacement, are not redox. And we haven't talked about that term yet. What you should understand is that the charges aren't going to change. So if it's NO3 minus over here, it's going to be NO3 minus in the product side as well. They should match. And then finally, PBI2. Based on this, I can see that the nitrates are going to cancel, the sodiums are going to cancel. What I'm left with in the overall is the lead 2 ion and the 2 iodide ions, making the lead 2 iodide solid. That's my net ionic equation. So if you're still kind of hung up on this, couple of places to go for help. First of all, make sure that you know your polyatomic ions inside and out. That's going to help. Second, we're going to be doing more of this on Wednesday, so you'll have a chance to kind of sharpen your skills with that before you get into the post-lecture, if that's what you want to do. Otherwise, last thing I have for you, as always, just a stoplight question for today. Do that on your way out of here, and I will see you on Wednesday. Have a great day.